There seem to be so many examples of groups that this seems to be a never-ending lecture. And if it wasn't enough, there is actually another way to find more examples of groups. Namely, once you have a few groups, you can make new groups out of the ones that you already have. So let's look at one way to make new groups from old ones. Suppose that I have n groups, G1, G2 through Gn, and they each come, of course, with their own binary operation, which I denoted by *1, *2 to *n. So I'm putting the subscript underneath the star to tell you which group this operation refers to. Then I'm forming a new group that is called the direct product. So this is called the direct product of G1 through Gn. So what does a direct product look like? It's a group consisting of n tuples of elements. So it's one element from the group G1, second element from the group G2, and so on. The nth element comes from the group Gn. So you get all the possible, you can put all the possible elements from G1 on the first spot, all the possible elements from G2 on the second spot, and so on. So if you look at all such tuples, then it turns out, well, that's first of all, that's a set, but it turns out that's actually also a group. If it is a group, I have to tell you what is the binary operation on that group, and it's just a binary operation that is made up of the binary operations on each of these. So if I take an element like this in the direct product, G1 is in G1, G2 is in G2, and so on, and yet another one, so H1 is in G1, H2 is in G2, and so on, then I have to tell you how to combine these two elements into yet another element of this direct product. So here's how I do it. On the first spot, I combine G1 and H1. Both G1 and H1 are elements of the group G1, so I can use the operation in the group G1, which was denoted by *1. On the second spot, I combine G2, which is in G2, with H2, which is also in G2. So this altogether gives me an element of G1, this gives me an element of the group G2, and so on. So in the end, I get yet another n-tuple, where the first coordinate is in G1, the second coordinate is in G2, and the third and the nth coordinate is in Gn. So in some sense, one sometimes say that you just take these tuples and the operations a coordinate-wise operation. That means that sort of you do, if the first coordinate belongs to G1, you do the operation in G1. The second coordinate is in G2, so you use the operation from G2, and so on. You can check, I'm leaving it to you to check that this is associative, and it really comes, the associativity comes from the fact that each of these operations is associative because G1 through Gn are groups to start with. What's the identity element in this group G1 through Gn, the direct product? So I'll denote it by E sub G1 cross ... cross Gn. That has to be an n-tuple. It has to be an n-tuple when the first coordinate comes from G1, the second coordinate comes from G2, and so on. So in fact, if I just take the identity in G1 and put it on the first coordinate, identity in G2 and put it on the second coordinate, identity on Gn, put it on the nth coordinate, you see that this does play a role of the identity in the direct product. Because if I now take any element, G1 through Gn, then according to this, you write it this way. Right, that's how you star two elements in the direct product. You just do things coordinate-wise. Well, but this is G1. Because the identity in G1 times any element of G1 gives you back that element. This is G2, and so on, and this is Gn. So, look, you took G1 through Gn, and you got G1 through Gn. So this is the identity element. I mean, you also have to check it the other way around, but the same thing works. Okay, let's erase this, because otherwise this equality here wouldn't be true. So, You just stack up identities from the different groups and you get the identity in the direct product. So this gives you a group. And in fact, I mean, I should also check that inverses are there, but you see, it's very easy to see that the inverse of that tuple is when I write it like that, where this is the inverse of G1 in the group G1, this is the inverse of G2 in the group G2, and so on. I mean, clearly, if I take that element and multiply it by G1 through Gn, because I multiply them coordinate-wise, I get on the first coordinate G1 inverse star 1 G1, well, that's EG1. On the second coordinate, I get G2 inverse star G2, well, that's EG2, and so on. So this really is the inverse of that. So, in other words, if I have any number of groups, I can form direct products and get new groups. So let's write down actually a few examples of that. And let's play with them a little bit. So, example 1, I'm going to take with addition and cross it with itself. Okay, usually people don't write it like this. They rather write it as Z cross Z. And you just, from the context, know what the operation is. This is, you could, of course, take a direct product of rings, as we discussed in the lecture about rings. But here, when I'm talking about groups, when I just write Z, I know Z is only a group under addition, not under the multiplication. So if I don't write comma plus, it's kind of understood that if I talk only about group structure on Z, then I mean with addition. All right, so how does this look like? So according to that definition, it's pairs now. AB, where A is in Z, and B is in Z. So all the possible pairs of integers. So so what's the operation? The operation is coordinate-wise addition. Right, so the operation, as it is in the direct product, it's the coordinate-wise addition. So in particular, right, so example 2, 7 plus minus 1, 2 would be 1, 9. I add these two and I add these two and I get that. There is a subgroup here, and of course the identity element, right, is the identity in Z cross Z is just 0, 0. Fine, let's just to complete this, let's write down an example of an inverse. So 2, 7 inverse is minus 2, minus 7, right? Because again, the operation is coordinate-wise addition, and surely 2, 7 plus minus 2 minus 7 gives me the identity, so 0, 0. Note that this group has a very nice subgroup. Namely, I can look at the following. A, comma 0, where A is in Z. I claim that this is a group under coordinate-wise addition. Well, no, this is the second coordinate is fixed, it's 0. So if I take two such elements, right? So if I take A comma 0 and try to add B comma 0, using coordinate-wise addition, that's A plus B comma 0 plus 0. So that's A plus B comma 0. A was an integer, B is an integer, so A plus B is an integer. And I still get 0 on the second coordinate. So you see that this set is closed under the coordinate-wise addition. In other words, the coordinate-wise addition defines a binary operation on that set. And it surely is a subset, so also now I know it's a subgroup of Z cross Z. Now in particular, 0, comma 0 is also in here, so the identity is there, and all the inverses are also there because the inverse of A comma 0 is minus A0. So this is actually a subgroup of this. Another subgroup will be take 0, we need to take 0 comma A. Right, so that's another subgroup. But these are not the only ones. In fact, how about this example? A comma A, where A is in Z. Is this a subgroup of Z cross Z under coordinate-wise addition? Let's see, if I take, so that means the same number on in both coordinates. A comma A plus B comma B gives you A plus B comma A plus B. So both coordinates are still the same, which means the binary operation restricts to a binary operation on this set. So in other words, the set is closed under the coordinate-wise addition. Secondly, is the identity there? Sure, 0, 0s of that form. Are the inverses there? Yes, because the inverse of A comma A is minus A comma minus A. So again, it has the same coordinates. So this is another subgroup of this group. Okay, let's look at some other examples. So example 2, Z mod 3Z cross Z. Okay, now I have to tell you what operation I mean here. So I mean this is addition, so I use addition here, and addition. This is addition of congruence classes, and this is addition of integers. So to be completely precise, I should have written this. But a lot of things in algebra are just done by understanding what things mean from the context. This is surely a ring, and it's a group under addition, just like any ring. Well, it's not a group under multiplication, because I would have to take the units, right, in order to get a group under multiplication. So it's kind of implied that I mean addition here when I write it like this, and same here. So for example, I mean, let's just add two elements to show you how this works here. So if I take, what's an element here? How about 1 plus 3z? An element there, how about minus 72? Okay, coordinate-wise addition. What's another element in here? How about just 3z? And another integer, how about 69? All right, if I add these two elements using coordinate-wise addition, this plus that is 1 plus 3z. Minus 72 plus 69 in integers, that's minus 3. Okay? So that is an element in Z mod 3Z cross Z. What's the identity in this group? So E what is it? Well, it's the identity here, so that's 3Z cross comma identity here, so 0. Finally, let's compute the inverse of, let's say, 2 plus 3z, comma 7. What is it? So that's just negative 2 plus 3z, negative 7. Which, by the way, is the same, of course, right, as 1 plus 3z. Negative 7. Do you see any interesting subgroups here? Yeah, I can see a subgroup. I can, for example, look at this, A comma 0 again, where A is in Z mod 3Z. Is this a subgroup? Surely, right? Again, by the same principle as last time, you can check. You know, adding two such elements will keep the 0 on the second element, and so on. So this is a subgroup. I could also do the other way around, namely I can look at 0 comma b, where b is in z. I'm sorry, I shouldn't write 0 here. I should write 3z comma b. This is also a subgroup. What about could I find some other subgroups? Well, last time I said I could just use this same element, Well, you see, this doesn't quite make sense in this case, right? Because Z has different elements from Z mod 3Z. So it's not the same group I take. There is a way to make sense of it in this situation. But just to be completely precise, if you don't take the same group on both coordinates, it doesn't quite make sense to say it's just do A, comma A. Yeah, because, well, the A on the first one lives in one group, so what does it mean to say to put A in the second coordinate as well? Just sort of as a word of caution here, you could just ask, oh, what if I didn't put 0 on the other coordinate, I just put 1? Is this a group, A, comma 1, where A is in Z mod 3Z? No, it's not a group, not under coordinate-wise addition, right? Because if I add two such elements, then using coordinate-wise addition, I get something in Z mod 3Z, but I get a 2 here. So no longer a 1. So this is not a subgroup, not a group. Let's do one more example. So example 3, where we're going to take mu3 crossed with Z mod 4Z. Okay, so here what operation can I mean on Z mod 4Z? I mean addition. Again, it's a ring, Z mod 4Z is a ring. Rings with just addition are groups, so that's not a surprising fact that I take addition here. But this is already predetermined, right? It's a cube roots of unity. The operation here is multiplication. So let's do an example. Okay, so what's a cube root of unity? So if I define zeta 3 to be cosine 2 pi over 3 plus I sine 2 pi over 3, then I can look at, for example, I don't know, let's do zeta 3 comma 2 plus 4z. This is an example of this element. Now I'm going to put a star here. Okay? It doesn't, like previously I put a plus, because on both coordinates I had addition in some sense. But this time on the first one I have multiplication, on the second one I have addition, so there's not really a good way to just decide if I should just put a plus or times there. I'm just going to put star, it's kind of a neutral thing. And then how about I do zeta 3 squared, comma 1 plus 4z. What do you get? So on the first coordinate you multiply, on the second coordinate you add. So you get, oh, zeta 3 times zeta 3 squared is zeta 3 cubed, so that's 1. Well, here I get 3 plus 4z. Okay? What's the inverse of zeta 3 squared? 3 plus 4z. Well, the inverse of zeta 3 squared is zeta 3 to minus 2, or in other words, zeta 3, right? Because zeta 3 squared times zeta 3 is 1. Remember, on the first coordinate we have multiplication, while on the second coordinate we have addition, so it's just minus 3 plus 4z. And maybe I should just, even before I had done this, I should have decided what's the identity in this group. Well, that's just the identity in mu3 under multiplication, that's 1. And the identity in Z mod 4z is 4z. I encourage you to play with these more. Think about maybe taking direct products of even more groups than just 2. Here in these examples, there were always only 2 groups that I took direct products of. You can take 3, 4. You can mix any groups. Direct product doesn't mix at all the operations, so you can just take direct products of any groups you know and sort of play with them. So add element, so combine elements using the binary operation. This skill will come useful soon.